We get started with introductions while people might still be joining. But yeah, thanks so much for joining us, Blake. Really excited to talk a little bit more publicly about the partnership that we've had and the brand new integration that we launched just 2 weeks ago, as well as following up on many of the exciting announcements that IBM shared at Summit last week. So we definitely have a lot to talk about today. And yeah, really appreciate your time and you being here. I know that we've definitely chatted many times over the last year or so, but never had this opportunity to kind of like sit down somewhat one-to-one, face-to-face. So yeah, thanks so much. Feel free to introduce yourself since I'm sure that for some people you might be a new face.
All right, so hi everyone, my name is Blake Johnson. I'm a distinguished engineer at IBM Quantum. I've been with the IBM team a little over 4 years now, and I'm responsible for what we call the Quantum Engine, which is effectively our low-level software stack, the thing that interfaces with our cloud service to process a sampler estimator request and prepare that for execution on the quantum hardware and then return it back to the cloud service to return to the end user.
Cool, yeah. And for those who might not know me, I'm Rowen. I'm a product manager here at Q-CTRL. I work on our error suppression products, and so worked definitely a lot with Blake on this recent integration that we've announced, where Q-CTRL is now surfaced as a performance management strategy within Qiskit runtime. I'll actually just kick off the webinar with a brief introduction to this product and just why we built it, as well as what and how people can use it. So I'll share briefly, but then, hopefully we spend the rest of the time just chatting between the two of us. Great. So as I mentioned, this was recently announced just 2 weeks ago. And so it's quite hot off the presses. Q-CTRL is now enabled as an option within IBM Quantum Services. So the reason that Q-CTRL has built this option, as well as the reason why we've been investing so heavily as a company into error suppression, is really due to the problem that broadly the entire industry faces today, which is that quantum hardware essentially suffers from performance degrading errors. And these errors are really due to the underlying qubits that required a careful maintenance of the state of superposition. And these errors affect all types of quantum hardware pretty much, and they basically obfuscate the correct answer that we're looking to achieve, as evidenced by the top graph right here. Typically, if you're not using any sort of performance management and you're not, and if you're pushing your device to the limits of what it can handle, you'll oftentimes see this sort of bottom graph as an output of the computer, which is a noisy distribution as shown here. And oftentimes that can be quite a frustrating experience for users who might not understand or might not have the options to mitigate this sort of noise. And that's why we've announced and launched this integration with the Qiskit runtime on IBM Cloud. With this single setting that is shown here, users can access Q-CTRL's performance management on any Qiskit runtime instance that is Q-CTRL enabled. And so I'll show a little bit later what exactly it means to have a Qiskit runtime instance that is enabled with this strategy. But essentially that means that any execution that is run on this Qiskit runtime instance will now have all of the benefits of Q-CTRL's error suppression pipeline. And this will simply work out of the box without any sort of change to your existing workflows. And what this unlocks is the benefits of having many of these errors prevented before they happen. And this enables oftentimes 10 times deeper circuits to be able to be run while still maintaining quality results and that clear signal of what the correct answer would be. In addition, this allows users to achieve 100x in time savings and simplicity. There's no sampling overhead, which means that users can get all of the benefits without having to do expensive post-processing. There's overall much improved overall time in reaching the correct answer with a high level of confidence. And so broadly, users are able to really reduce the amount of overhead that they have to expend getting to the right answer. And then users are able to achieve 1,000 times improved performance. This performance is measured within accuracy in benchmarks. And all of this information can be viewed in our peer-reviewed technical manuscript, which is cited below and shows how we've achieved these results on a number of different benchmarking algorithms. And so how Q-Control achieves these incredible numbers is through a comprehensive error suppression pipeline that performs many of the steps from an initial compilation to actually changing the circuit, not performing any sort of underlying changes, but replacing gates, reducing the depth. Everything that we do is an identity transformation, meaning that the actual what is running doesn't change. And everything that we do is also completely deterministic, meaning that within a single run, the user receives all of these benefits, and they simply get the results back and they see the improved result as we aim to achieve. So I'll quickly also demonstrate how exactly this Qiskit runtime instance would be created and how users can take advantage of this option. So if I go to the IBM Cloud Portal, as mentioned, this option is offered on Qiskit runtime instances through IBM Cloud. And so it'll be surfaced on pay-as-you-go devices. And as we'll see here, if a user is creating the Qiskit runtime instance, they have an option to select different plans. The standard plan comes with device access. And as you can see here, the cost of the Q-Control Embedded option is baked into the original pricing. And so there is no additional costs required in order to choose this option. So the user, once they select the standard plan, they can actually go ahead and simply select a performance management strategy. The first one is the performance management that is offered through IBM, offering 3 different resilience levels. And then the other option here is this Q-Control automated error suppression option. So that's what we're really excited to announce, and that's how users can unlock the value that was previously shown and is cited in our technical manuscript. And so once users do that, they can simply create this instance. They would then copy the cloud resource name. And once they initialize Qiskit runtime service with that instance, you can save it as an account on your device locally. And then anytime you're using that service account, then you would never have to specify any additional settings later on. So that's essentially the integration in a nutshell. And so we're really excited to have this option available. I want to spend the rest of the time really just chatting with you, Blake, and hearing about how users will use this to actually achieve beyond what has been previously shown, which is, the goal of both of our companies.
Sure.
Yeah, first of all, let's just talk a little bit more about the exciting updates last week announced at Summit. I think there were quite a few, but definitely there were some things that are really launching us into this era of quantum utility. Can you talk a little bit more about what utility scale demonstrations are and what companies can do to get there?
Sure. So yeah, as Rowen mentioned, we had a lot of announcements, a lot of content from Summit last week. And I can only sort of scratch the surface in the time we have today, but I encourage you to take advantage of the resources that are available both on our website, ibm.com/quantum, and also on the IBM Research YouTube channel, where all the sessions are now posted, the videos from all the sessions. So you can kind of enjoy that content at your own pace, or look at the blogs and other resources where you can get summaries of the main highlights from each session. So the the overall theme of our quantum summit this year was the era of utility, which we firmly believe that the sort of we have as a community, as an ecosystem, have now entered. And this term of utility may be less familiar to you than terms like quantum advantage. What quantum utility means is that quantum computers can now do tasks beyond what is possible to replicate with brute force classical simulation methods. And that differs from quantum advantage because there may still be, depending on the problem you're addressing, classical simulation methods or classical approaches to solving problems, which are not trying to directly, in a brute force manner, simulate the effect of the quantum calculation, but doing some other kind of calculation. But because quantum computers can now do things beyond what a classical simulator can do, they truly become tools for research, right? They become something that you can, is just like any other tool, any other way you can approach a problem, become a perfectly legitimate way of actually trying to approach doing scientific work, computational science work. And that's a really big thing. I mean, it's a new thing for quantum, where we're no longer just trying to study the quantum computer to understand how to build better quantum computers, but finally able to use quantum computers to do work. And the thing that really kind of enables the era of quantum utility is a number of sort of performance enhancements, right? It's better hardware that's faster, lower error rates, it's more reliable, it's more stable, working with various kind of error suppression and mitigation strategies to enable working at circuits that are kind of at the 100 qubit scale and beyond.
Yeah, it's a hugely exciting stage that we're entering, an era in the industry. Quite a bit has been done. I know that even looking back at Summit a year ago, the progress is monumental. At this summit, I think a huge focus was put on error mitigation, and that was demonstrated in many of the utility scale experiments that were shown and have been really put on and displayed by IBM in the past few months. As you know, the Q control option is error suppression, and so the way for the users who might be less familiar with the differences, the way that I like to phrase it simply is that error suppression is this pre-processing and preventative measure that you can take to prevent errors from happening at runtime, and then error mitigation is a post-processing and corrective measure that can find errors that happened already and then correct for them later on. Out of curiosity, where do you see those playing together, and why are error suppression methods needed to unlock this era of quantum utility?
I mean, so the working at utility scale has a number of prerequisites, the most important of which is being able to successfully execute and get reliable answers out of circuits that are kind of beyond brute force simulation. So we're talking about 100 qubit circuits effectively. I mean, brute force simulation methods basically start to fail right around 50 qubits. There are ways with access to the largest supercomputers in the world, you can stretch into the low 50s, low to mid 50s. But once you get up to 100, I don't think anyone will admit to having a realistic approach to doing sort of brute force simulation at that scale. So the first step is kind of getting towards reliable circuit outcomes at that scale. And error suppression basically means that the outcome of any particular shot, any single execution of that circuit, you'll have reduced the likely presence of errors in that circuit. And error mitigation is sort of a technique that kind of layers on top of that to look at sort of collections of multiple circuit executions where you have some way to manipulate the noise. If error suppression is just sort of bringing the noise level down, if you then have ways to kind of change the noise or have a really good model for the noise, you can then look at sort of collections of circuit executions to be able to infer something about what would happen if you had even less noise. And so those techniques kind of work in complementary ways to try to get you towards better, more reliable and accurate estimates, accurate outcomes from a quantum circuit execution.
Yeah, definitely. Thank you for summarizing that in a much more efficient and succinct way. And where do you see kind of the next steps going in terms of how Q-Control's error suppression works with the IBM offered error mitigation?
So right now the offering, right, the user has to choose, right, between the Q-control techniques, which are really about, as Ron has mentioned, they're about error suppression, driving down errors in single execution. And the IBM methods have focused more on error mitigation, right? This sort of looking at collections of executions. I think there's going to be an interesting era of exploratory work as we kind of find the limits of those different methods for suppressing errors or for reducing errors. But clearly, there's an interesting opportunity to combine error suppression methods with error mitigation methods because the cost of error mitigation, while it maybe allows you to get to even larger scales, it comes with an overhead for that mitigation. That overhead is proportional to the underlying error rates. So having lower error allows error mitigation to scale to larger sizes more cheaply. So we're already sort of contemplating ways that that users might be able to combine these technologies in the future. And we don't have an answer yet, but it's certainly an interesting thing that we need to explore for the future.
Yeah, definitely. Our team is also very excited to work on this area of research and see how users can end up layering on these methods. I really like how you described the fact that error suppression can really reduce the amount of overhead that is required by error mitigation. And so we're excited to kind of show and quantitatively measure, how much that benefit can be achieved and expand on that there. What sort of additional utility scale demonstrations are you excited to see unlocked by some of these error suppression methods and this integration?
Yeah, I mean, I guess time will tell. I can say one of the things was exciting, right? Like we at IBM would say that we sort of provide the first evidence for this era of quantum utility this summer when we published our paper in Nature that was about a kick-dicing model. So it's looking at the time dynamics of basically spins in a lattice, which is a model which is reminiscent of many ways that we use to model certain kinds of materials, right? So it looks kind of like a material science kind of simulation method. But right at this point, it's sort of I think that opened the floodgates. And at Summit we showed 11, actually there's 13 total presentations, but there was 12 additional examples that were shown that were beyond the 50 qubit scale, from everything from optimization to high energy physics. So things that are more close to sort of directly recognizable sort of business problems to things which are more about sort of fundamental science and scientific research. So I think there's a lot of exciting examples, but I guess, Ron, do you want to say some more about the work that the Q-Control team showed at Summit?
Yeah, definitely. Really excited to see all of the demonstrations that were at Summit. I was lucky enough to be there myself and witness them. Our CEO, Mike Biersick, he did talk a little bit about our work in the QAOA domain. So for folks that weren't at Summit and didn't see the results that Mike showed, we recently have been looking into QAOA and implementation on the max cut problem. So this is an interesting problem that's often studied in mathematics as well as relevant to many real-world scenarios. The paper that we are basing off of and reproducing showed max cuts up from 26 qubits to 32 qubit problems. And within this paper that was ran on an alternative hardware provider, the cut was found in some scenarios on the 26 qubit and the 28 qubit examples. However, it struggled to find the correct answer on 30 qubits and 32 qubits. We sort of replicated these results using similar randomized graphs. And we were able to show that Q-Control on top of IBM hardware and IBM Quantum Services was able to achieve the correct max cut for all 4 of these instances. So pushing from 28 qubits all the way to 32 qubits. And the benefit, in addition to finding the correct answer, was also that the Q-Control solution was able to implement the full hybrid execution, meaning that there was no classical pre-processing, as was demonstrated in the existing published paper, where the initial parameters were pre-computed using classical time. And so executing this full hybrid execution on IBM hardware required actually 30% wall clock time with this combination of our tech stack versus a single execution with that sort of pre-compilation on the alternative. And so we were really excited to see that Q-Control on IBM could already yield benefits in these sort of larger problems, especially when contrasting with existing published results. And we continue to push this a little bit further. So Q-Control was actually able to show that even for problems up to 50 qubits for this max cut problem, we were still able to find a very high quality solution, which was extremely close to the largest cut. And so the likelihood of finding this, very high quality solution is very small in this huge problem space or the huge solution space that exists with a 50 qubit problem. And so this demonstrated that we're able to really push the results to very high quality answers, even with these pretty large problem sizes, and achieve 32,000 times performance boost over the brute force methods. And so really, as you were talking, Blake, about the, utility era and what that means, achieving better results than brute force solutions or classical solutions, we're really excited to see that the combination of our technology will definitely unlock this value for many of our users, and also excited just to see what people end up coming up with in the next year and beyond as we're entering this really exciting time. And with that, I also wanted to kind of ask a little bit just about, how this relationship really unfolded. Why did IBM Quantum decide to open up the platform to Q-Control? As far as we know, this is kind of the first integration of this kind, and we're really, honored to be part of it. But would love to hear kind of from your end what that justification was.
Well, Q-Control was one of the sort of early members that joined our IBM Quantum Network startup program, where, which is the IBM Quantum Network as an ecosystem of users, of institutions, of businesses, both small and large, that are either eager to consume quantum or that are sort of building out products to be part of the quantum ecosystem. So we've had dialogue with Q-Control for several years now, looking at what they were trying to develop. And I guess the team has had results that were intriguing and interesting for a while. And they've been been willing to kind of be put through the ringer as we kind of asked them to test and stress their methods through in many different ways, right? We were worried that maybe this set of techniques only apply to a very small fraction of possible use cases, but they were able to show us that In fact, there's a fairly diverse set of cases that it seemed that this technology works. And so with that, we kind of got to a point of comfort of putting this technology in front of our users to see what they would do with it as well. And so that's kind of how we've gotten to the point of being able to take this step together with Q-Control.
Yeah, it's been definitely an exciting journey. I know that since the joining of Q-Control at the IBM Startup Network, there have been huge progress on both sides, and we wouldn't have been able to achieve a lot of the results and capabilities that Q-Control has built without having this sort of open platform that IBM has built that, you know, has all of the access to these underlying capabilities of the device, and the flexibility for us to really build on top of what is already a very powerful platform.
That's a good point. I mean, something I will say is that, you know, we've often developed tools and strategies that are really geared towards flexibility, really kind of allowing our users to kind of turn all the knobs, change as many things as possible. And what was maybe a bit different about Q-Control's approach, right, is it's turnkey, right? Like there's no configuration, you just turn it on. Um, and and so it's a very different approach, and it seems like also a way that maybe would appeal to a different audience, a new audience, and so that also was a good reason to kind of take the risk of taking this step together.
Yeah, definitely. I think it's a great point. I think that even at the summit demonstrations, we saw quite a variety of different backgrounds of people who were doing those sort of utility scale experiments, many with more quantum or less quantum expertise. And so I think it really speaks to the diversity of people who are really running on quantum computers now. And so having more turnkey versus more flexible solutions definitely makes sense to meet users where they are. Great. Well, I also wanted to ask some fun questions while I have your ear. I have heard that you and Mike, RCO, have crossed paths in past life professionally. When was that, and what was that like?
Yeah, so Mike and I go back a long ways. We met while we were both students, while I was an undergraduate and he was a grad student. At the time, I was this was my first sort of experience working in a physics lab. I was working on studying electrical transport in one-dimensional superconductors. So making little nanowires out of superconducting material and studying the transport properties. And Mike at the time was studying quantum dots, which is another quantum system that some teams have used to make small quantum processors as well. But I think at the time Mike was studying noise, I think, in quantum dots. In any case, I was the task that my PI had been given to me was basically to fabricate these devices. Eventually we'd go to measure them. And you know, so I learned all about sort of nanofab. And one of the most annoying steps for me, I think it's an annoyance for every grad student that has to do device fabrication, is wire bonding. You have to attach you know, little micron scale wires to your device from whatever the microstructure is you've made to the package it's in. And the university had a wire bonder, and this device that sort of, you know, allows you to translate macro manipulation of like a controller to the kind of microscopic scale in the clean room. But this wire bonder was constantly broken. It never worked. But Mike's PI had his own wire bonder. Like he knew that the one in the clean room was broken all the time. So he bought his own and it was in his lab. And he didn't let anyone that wasn't in his lab use it. But Mike helped me out and got me access to their group's wire bonder. And that's how sort of like we first got to know it. Mike also really enjoys talking about politics, and so he would and there was the grad student I was working with also enjoyed talking about who's actually a postdoc, also enjoyed talking about politics. And so I would come in every day, and those two would be sort of hashing it out over their latest like Howard Dean fiasco, whatever. And so I sort of got to know Mike personally as well as like professionally at the same time.
That's so funny. I've actually not heard that story before, but it's really cute to hear about the origins of the relationship. And I'm glad that, however many years later, you could come back and, spend time together professionally again. And hopefully the favor has been returned at this point. Yeah, cool. Yeah. And then just out of curiosity, is there anything that the IBM Quantum team has achieved so far that you really didn't believe or did not know could be done?
Um, I think there's like uh small victories that have happened that surprised me. What I would say though is uh more big picture view. Uh, uh when I started out in this field, I guess back in um 2003, 2004, um, everyone started, it was one of those things that like we were just, developing individual qubits at the time. And there was this question of like, you constantly get the question about like, when is quantum computing going to be a reality? And at that time, it always was like one of those things, oh, it's like 20, 30 years away. But this is so cool. I'm willing to work on it anyway. And sort of over time, sort of my estimate of like how long it will be till quantum computing is real is shrunk faster than time has advanced. Here we are about 20 years later from when I started it, and quantum computing definitely is real. Um, and so like I don't know, the rate and pace of change has really astonished me.
Yeah, that makes total sense, especially given, the roadmap that IBM announced last week. That was definitely a surprise to me about how, the 10-year roadmap is shaping out to look, and just the ambitious plans that IBM has in mind for the next 10 years. But, the track record definitely goes to show that those plans are well formulated and I think likely to happen. So very much kudos to all of you there.
Thank you.
I'd like to open up the floor to Q&A. I've already kind of asked you a bunch of questions, some hard hitting, Blake, I'm sure. But yeah, definitely if folks are curious about anything else about the integration or the partnership, now would be the time to ask. I have another fun question for you, Blake. What is your favorite feature that IBM has put out in the last year that possibly that you've worked on and possibly that you've seen another part of the company produce?
That's a good one. Well, I mean, there's, I have a lot of answers to that of the things that I think are pretty cool. But one thing that I've personally involved in, right, is in find um, helping define and expand the kinds of circuits that are possible to execute on quantum hardware. Uh, you know, uh, when IBM first put quantum hardware online, you could communicate with those systems using OpenQASM, and they sort of, which quantum assembly languages were a thing that existed, but OpenQASM was an effort to kind of formalize those with a real specification as opposed to just like examples in a textbook or examples in a paper. But OpenQASM was kind of a product of its time. The circuits that were, the control systems that were possible to use that at that time didn't anticipate the ability to use measurement data in real time. Right. So everything kind of had to be chosen in advance. These are static circuits. But through a lot of effort, the control systems have gotten to the point where they can manipulate values and data in the kind of sub few hundred nanosecond timescales that are necessary to use measurements to influence the source of computation. And so that motivated us to work with the community to update OpenChasm for this new era of dynamic circuits. And so we kind of started that with a new specification for OpenChasm, that's OpenChasm 3, but that is which you can directly execute on IBM Quantum hardware. But we've kind of percolated that through the Qiskit tooling as well. In the past year, Qiskit has gotten a lot more expressive in the kinds of circuits you can build, so that circuits can have branches and for loops and while loops, and you can make sort of Boolean expressions on classical values, and all that kind of works, and it's representable in Qiskit, and I think that's really cool.
Yeah, we're definitely excited to experiment more with dynamic circuits. We were kind of, an early adopter, of course, when it came out. And I think that the capabilities have really grown even more powerful within the last year. So that's definitely also another area of exploration and research for us within the next year to see how we can bring those capabilities into our pipeline as well. Great. So we have some questions building up now. One is, where can we find more information on how to get started using the new integration? I think one of the best places would be Q-Control documentation, where we have some of the get started materials in more in-depth topics and information, as well as some tutorials and guides. I'll send the link here in the chat where in the answered Q&A, you can go and see the link. But the information is also available within the IBM Quantum and IBM Cloud documentation for Qiskit runtime as well. Another question, does Q-Control work with AI? If yes, could the error mitigation based on AI be further optimized for specific algorithms instead of using a general procedure? So Q-Control does work with AI. We incorporate AI into a couple different areas in our pipeline, including the layout selection component, where we use machine learning to pick the qubits on the hardware that will be used and corresponding to the qubits that were designated in the circuit. So that's one place. And then we also use AI for a gate replacement technique, where we are replacing gates within the circuit with ones that are going to be more efficient and reduce error based on the device quality and the readout values that we get from the backend data. All of this is included in the technical manuscript where I linked in my short presentation when we talk about the full pipeline and the methods used there. In regards to error mitigation based on AI, we actually try to make our pipeline as general as possible so that, as Blake mentioned, everything can be run through the same pipeline. There's no configuration. We've actually seen that with the specific pipeline, less configuration is actually better. That when users try to, change different elements or, try to customize our pipeline, it actually generates oftentimes more noise than, say, the specific pipeline we've built out. For error mitigation and introducing AI, I think that this is definitely a topic of exploration for, both of our companies. I think that there was a really interesting paper that I saw at Summit about how ML can be used to improve error mitigation and reduce the overall overhead. Blake, maybe you want to talk a little bit more about that paper and how IBM is planning to implement that.
So we actually have a lot of explorations that are going on, sort of applying AI to quantum. one of the things which actually is already available, not just as a paper, but as a service that our premium customers can access is a service that does transpilation, circuit transpilation or rewriting that uses a model, an AI model that was built from a reinforcement learning method. So it takes some of the complex parts of circuit rewriting, like swap networks or uh, converting a Clifford group operation, which is a kind of abstract mathematical transformation on qubits, into a concrete circuit representation. And it can do tasks like that better than our sort of human developed heuristic methods that are in Qiskit. And so that's a new service endpoint that you can hit to get back circuits that are between 20 and 50% shallower or using fewer gates than the methods that are in Qiskit today. So there's a number of, I think, powerful there's a bunch of low-hanging fruit, I guess I would say, in terms of applying AI to quantum, and we're really excited to see what else we can do in that space.
Yeah, definitely. I think it's an exciting area of exploration all around in the industry. The next question is, what near-term real-world use cases do you believe will emerge soon as IBM's hardware continues to scale in combination with Q-Control's error suppression toolchain? Yeah, maybe Blake, I can let you answer first, and I can also give a response.
Sure. So one of the major changes in how we talk about the future of IBM quantum systems is that we're beginning to label our offerings in each year with the size of circuit that users should expect to be able to reliably execute. So if you look at what we're promising to deliver in 2024, for instance, with the Heron systems, is that those will extend to be able to execute circuits with up to 5,000 gates. That's that is a fair number of gates, but but it's not so many that that you can do arbitrary computations, right? And so like when we're thinking about the near term of what will be successful in that kind of hardware, we have to still think about algorithms or encodings of our problems into quantum hardware, which have a cheap or very efficient encoding. And so in particular, things that sort of directly take advantage of the fact that qubits are like spin systems makes them really efficient in modeling things like glasses and certain kinds of materials, because you can imagine it like because like there's almost a zero overhead encoding for going from your model that you want to study to the system of qubits in the geometries that we lay them out, or that we couple them. But I think as we continue to scale from circuits with 5,000 to 10,000 to 15,000 gates and so on, just the aperture of what problems will be successfully executable will just grow over time. And so particularly once we get towards error-corrected hardware in the further future, really then the application space should really just dramatically expand.
Yeah.
What are you excited about, Rowen?
For us, we're definitely exploring many use cases within logistics and optimization, as well as next year, financial use cases will also be a big focus for us. So at Summit, I did talk a little bit about a real world example that we executed with the Australian Army. And that was an example of using quantum optimization for convoy routing. So it's a very difficult problem, especially with dynamically changing variables such as traffic patterns and potential battle scenarios. And so being able to route a larger amount of vehicles than what is classically now possible is definitely something that we are very excited about, and we think is a potential for near-term real-world use case. Even 120 convoys can take over a month of classical computation time to route. So that really brings down the threshold of what is needed to be better than classical. So that's definitely an exciting area. In finance, I think that there are a lot of interesting both optimization and quantum machine learning use cases. Quantum machine learning, I've seen a lot of people rejuvenate their excitement in the past year or so, given that devices are really getting larger and quality is getting better. And so I think that the use cases such as what HSBC showed about fraud identification within finance, those types of machine learning use cases are also really promising. Next question is, does Q-Control plan to support ternary quantum computation on IBM devices using Qtrits? So actually, Blake, maybe I'll ask first about what IBM devices support in this realm.
So currently, right, we offer pulse level control on all the hardware systems that are available today. With the exception of our exploratory systems. So all the core systems, which are principally now Falcons and predominantly Eagle processors, which are the 127 qubit processor, all support pulse level control. And so there's sort of everything you need from a signaling perspective if you want to access higher levels of okay. Step back a moment. The qubit that we use in IBM Quantum Systems is something known as a transmon. A transmon is actually it's basically it's like a harmonic oscillator, so like an LC resonator, but where the inductor in that LC circuit is nonlinear. And so if it were truly just an LC resonator, it would have energy levels which are equally spaced, and so that would not be possible to address just a single pair of levels. So you couldn't use it as a qubit. But the fact that the inductor is nonlinear means that the levels become unequally spaced, and that allows us to address just the bottom two levels and treat that system as the qubit or the quantum of our quantum system. But the other levels are still there. And so the fact that you can send pulses at different frequencies means that you can address the 0-1 transition of the transmon independently from the 1-2 transition and so on, or even drive multi-photon processes that directly couple the 0 state to the 2 state, for instance. So all that's possible from like a signaling perspective. And then it's just a matter of like, do you build extra tooling and software to make that convenient? I mean, there's been various papers, even some from our team, that have looked at doing QK control with our hardware. I believe actually sometime in the next month or two, you should see related to one of those papers, a little package in the Qiskit community GitHub organization that has some convenience utilities for doing Qtrit like control. I will say that this isn't like I wouldn't seriously consider this as like how you should operate or think about algorithmic or utility scale work. This is really more about sort of understanding physics of these devices, or if you're interested in sort of quantum information science and quantum control. But because effectively this two-state, in particular the way that we build our transmons, we don't particularly optimize to make this 1-2 transition stable. And so the coherence, for instance, in the second state is much worse than the coherence of the first excited state. And so it's while it's all possible, it's not really relevant to utility scale work.
Yeah, I would say that first of all, excellent explanation of the underlying capabilities. From the Q control side, we definitely try out quite a range of the, really expert level capabilities that IBM offers, and stay very close to the new features that are being released. And so we tend to see what makes sense within our error suppression pipeline and figure out whether or not there are benefits in terms of the goals that we are achieving, which are also typically in line with pushing further towards, these utility scale experiments. And so if we see ways of incorporating capabilities such as this into the pipeline, we do build them, or we build on top of them. But with, the more underlying capabilities, exposing them through our pipeline is, something that we don't typically intend to do for, say, users. That's oftentimes where we leave the platform level features for IBM to fill in those gaps. We got quite a few questions, but I think we'll try to pick off a few more. Regarding what software frameworks do you see companies using to solve current problems? I think one easy one, of course, that we can both say is Qiskit. I think people, they're building on top of the frameworks that are available, but I mean, I think IBM even showed metrics that show that Qiskit is 80% preferred by most programmers of quantum computers.
That's right. I guess obviously Qiskit is my first answer too, but something that we're really trying to enable with the sort of the utility era is, and when we're starting to attract computational scientists to use these as tools to enable the research, right, is wanting to think about how do we make what quantum computing fit within frameworks that are already familiar, right? So if you're a computational chemist, how do you use quantum within a computational chemistry toolkit that you already use, right? So towards that end, one of the things that we presented in Summit is something we call Qiskit patterns, which is basically a recipe for organizing code that uses quantum in a way that it kind of fits nicely. It can slot nicely into a workflow that you're already using, right? Because it basically starts with a classical description of, classical inputs of the problem you're trying to solve, and ends with a classical outcome. And that sort of ends up as something that becomes a step you can inject in a workflow in whatever other tooling you're already using. And so, we introduced this as sort of a concept with a bunch of examples, and you can see a lot more of those examples on the documentation on docs.quantum.ibm.com. But it's in the docs and then the tutorials as well. And so I'm very much looking forward to seeing people kind of expand on that idea and see ways that they can kind of embed quantum within frameworks that are sort of relevant to their application domain.
Yeah, I will say that also Q control definitely tries to also expose our capabilities within the frameworks that maybe higher level front end applications as well as development platforms are building out. And so on a related note, I see that there's a question about performance enhancement being available through third-party platforms. Or our performance management offering being available on third-party platforms. We're definitely looking to expose this with our partners that are building sort of these development platforms and solution frameworks to also have them, if they have IBM Cloud as a backend offering, then we also would love for Q control to be an option as users of these platforms are executing circuits on IBM Cloud to be able to turn on this performance management strategy. We have another question about some exciting areas where the partnership could go next beyond error suppression. I think that we have definitely talked a little bit between within our partnership about some exciting areas for next year. I don't think that we can expand on them just yet publicly, but I will say that we're definitely all excited to move towards this era where users can leverage the capabilities of quantum within their functional domains. And so similar to Qiskit patterns, and the idea there is really to have building blocks that users can reproduce and replicate without necessarily having to completely build from scratch each time. And so I think that that's also an exciting area where error suppression can play a part, but our partnership can also continue to expand. Blake, did you want to add anything to that?
No, I think it's great.
Great. I think we're pretty much at time. I know that there's still quite a few questions left, but I'll be mindful of everyone's time. If you do have additional questions, I think we'll save these. I'll try to answer people directly as much as possible. But we can also send out some information after the webinar about how you can get in touch with us and continue the conversation. I'm definitely happy to chat more, and I'm sure I'll offer up the same from Blake, that we're happy to answer questions from our very interested base. Cool. Thank you so much, Blake, for your time. This was a really fun discussion. Hoping that you enjoyed it as well. And yeah,
Thanks.
enjoy your holiday season.
Same to you.
Cool. Thanks so much. Thanks everyone for attending.